This is Vodcast 5A. In Unit 5, we're going to be talking all about ions and ionic compounds. There are going to be 4 videos total in Unit 5. The first one we're going to go over is just basics about ions. The second one will be names and formulas of ionic compounds. The third one will get into how to name acids. And the fourth video is going to be all about salts. So first we have to talk about what an ion is. Here's your definition. An ion is an atom or group of atoms that have a net electric charge. In Greek, ion means the ones that move. We talked a little bit about this before. How do ions have this electric charge? Well, they can either gain or lose one or more electrons. It's going to be all about the electrons. Here we've seen this picture before. Here's my neutral molecule. Neutral meaning it has the same number of, in this case, protons, neutrons, and electrons. What really matters are the protons and the electrons, the positive charges and the negative charges. If it's neutral, they have to balance out. If I lose an electron, here I lost an electron, now I only have a proton and a neutron, that ion is called a cation. It has a positive charge. There are more positives, there are more protons than electrons in that ion. If you look up top, here's my neutral molecule again. If I add an extra electron, because electrons are negatively charged, I now have more electrons than I have protons. My overall charge is going to be negative, and that is called an anion. So we're going to have charged particles. They're either going to be positive or negative, and they have to be whole numbers. Why do they have to be whole numbers? Well, we're counting the difference between electrons and protons. We're going to change our electrons. We're either giving away electrons or we're gaining electrons. You can't give away or gain half of an electron, so we're always going to have whole number charges. And the charges mean how many electrons I either gave away, cation, or gained, anion. There are simple ions. Simple ions are just that. They're very simple. They have a single charged atom. So these you'll find on your periodic table. Here's an example of hydrogen. If hydrogen loses its one electron, it has a 1+ charge, and it's the hydrogen ion. You can have positive ions. These are the cations. Remember, they lost. Here's an example of an anion. Sulfur likes to do what? Well, in this case, it gains 2 electrons, so it would be sulfur with a 2- charge. Other examples, another cation, aluminum, likes to lose 3 electrons, so aluminum would have a 3+ charge. Nitrogen likes to gain 3 electrons, so it would have a 3- charge. Those are simple ions from the periodic table. They are also complex, or what we're going to call polyatomic ions. Polyatomic, poly means many atoms. Different atoms that consist of a group. So here's my whole group. Now I have nitrogen and oxygen. They are bonded together, and that whole group of atoms has a net charge of -1. Not just the oxygen, but the group of nitrogen and oxygen put together has a negative net charge. These are called polyatomic ions. If you look in your folder with your periodic table on the inside, there's a list of common ions. There are some simple ions from the periodic table, different metals that can form different charges, as well as some more polyatomics. Some examples of polyatomics. Ammonium is NH4 with a 1+ charge. Nitrate is NO3 with a 1 minus charge. This looks like this one. This is nitrite. This is nitrate. So there's lots of different examples on your sheet. Cations and anions again. Cation. I lose electrons or I lose negative charges. So overall, I now have a positive net charge. I have more protons than electrons in a cation. I have an overall positive charge. In the anion, here's another picture. This is the opposite. Now I have more electrons than protons, leaving me with an overall negative charge because I gained electrons and my electrons have a negative charge. But since things in nature are neutral, ions exist as groups of cations and anions that form together. The sum total of their charges always has to equal 0. If you have a +1 cation, you need a +1 anion. If you have a 2+ cation, you need a 2- anion. They always have to cancel out to equal 0. So this is how we're going to write formulas to balance them out with their charges. Let's talk about salts again. In the 19th century, water in which salts were dissolved conducted electricity. We talked about this briefly before. The electric current could separate these dissolved materials into their components. How is this? Why is this? Same reason you're not supposed to be going swimming in a thunderstorm. If there's lightning, why? Let's use this diagram to help us explain. So in 1884, table salt dissolved in water breaks up into electrically charged ions. Here's our table salt. This is one we know. Sodium and chlorine. Why does sodium have a little plus and chlorine have a little minus? Well, let's look at these diagrams. Here's my sodium atom. Sodium is number 11 on the periodic table. That means it has 11 protons and 11 electrons. When it's an atom, it's totally neutral. It has 11 positives, 11 negatives, and all is good. But what happens when this sodium comes in contact with this chlorine, who has 17 protons and 17 electrons? Again, the chlorine atom is stable, or it has a net charge of 0. It looks like it should be stable, but what's missing? There's this one little spot right here, and we know chlorine, since it's a halogen, wants to gain 1 electron. Sodium has 1 valence electron because it's from which family? The alkali. The alkali metals and the halogens like to react. Why? What do? Sodium, its 1 valence electron, gives it up to chlorine. Chlorine now has an extra electron, 18 electrons, but only 17 protons. That's how it gets its 1 minus charge. Sodium loses that electron. It loses that whole third shell, third ring of electrons. It now only has 10. 10 negatives and 11 positives is how we get our Na1+ ion. So when there's some kind of electric current, such as a battery, you have a positive end of a battery and you have a negative end of the battery. All the negatively charged things, all the chlorines in this case, are going to be attracted to this positive end, and all the positives, the sodiums in this case, will be attracted to the negative end. That's how we have this movement. That's how water conducts electricity. If you have dissolved particles in there that are charged, so electrolytes or ions, they can move with a current, such as a battery, because the sodium moves in one direction, in this case to the right, towards the negative side, and chlorine moves in the opposite direction, in this case to the left, to the positive end. This is a little more simplified diagram of exactly what happens. In common table salt, the sodium cation, we now know as Na1+, is neutralized by the chlorine anions, we now know as chlorine 1-. Sodium likes to give away one electron, chlorine likes to gain an electron. So here's my sodium with its 1 valence electron, and here's chlorine with its 7 valence electron. Again, this is simplified. It doesn't show you all of the inner electrons, because sodium would have 2 on this inner ring and 8 on the blue middle ring. We're just looking at the valence electrons right now. In its valence shell, sodium has 1. It likes to give that 1 to chlorine because then they're both more stable. Chlorine slightly increases its size because now it has 8 full shell valence electrons. Sodium loses this whole shell. Sodium actually shrinks in size because now it goes from 3 electron rings down to 2. And sodium's now happy. Why? It had those 8 electrons in the second ring that are now its new valence shell. So sodium now also looks like a noble gas, and it's full with its 8 valence electrons. More ion basics. Ions have the exact same nucleus as their parent element, as the atom. The only thing that's different are the electrons, the electron configurations. Because the electron configurations are different, they're going to have different properties. You eat table salt, sodium and chlorine ions. You would not want to eat pure sodium metal or pure chlorine gas. Simple ions. We talked about simple anions. Simple anions are generally the nonmetals. Why? Anion means gaining electron. Who wants to gain electron? Things on the right side of the periodic table. Simple cations. Cations lose their electrons. Metals tend to lose their electrons. Anything on the left side of the periodic table tends to lose electrons. We left the transition metals alone for a little bit last unit. Here's some details about them. They do form stable ions. They do not fit the same pattern, though, because they have these crazy d orbitals. So it kind of gets messed up with the S's and the P's. What we have to know is they are all cations except for rhenium. They are all cations. That means they tend to lose their valence electrons. They give them away. And most of the transition metals can form more than one different cation. So that's what you'll see in your chart. Copper is an example. Copper can have a 1+ or a 2+ charge. Copper can be stable giving up 1 electron or 2 electrons because of how these d orbitals jump to fill in the S's and the P's. Again, this is all on your chart. You can just look it up, the different charges for each of the transition metals. Ions that have a noble gas configuration are, here's your vocab word, isoelectronic with another atom. Here are 3 examples: the sulfur ion, an argon atom, and a potassium ion that are all isoelectronic with one another. They have the same electron configuration. They each have 2 in the first ring, 8 in the second, and 8 in the third ring. Isoelectronic atoms are different sizes, even though they have the same electron configuration. Why? Here they each have 18 electrons. Sulfur with a 2-, that means sulfur did what? It gained 2 electrons. Argon has no charge. It's a neutral atom. It normally has 18 protons and 18 electrons. The potassium ion has a 1+ charge. That means potassium lost 1 electron. Potassium lost its 4th. If you look at potassium, it's in the 4th row. Potassium lost its 4th outer shell to come back down and look like, be isoelectronic with argon. Now, thinking back to Unit 4 and our trends for the periodic table, which of these would be the smallest and the largest? Why do they have different sizes? Even though they all have 18 electrons, who would be the smallest and who would be the largest? What was the trend for the periodic table that we said going from left to right on the periodic table, the radius actually decreased? Why did it decrease? It decreases because as you add more protons, there's more nuclear pull, so the nucleus can hold its electrons tighter. So if sulfur has 16 protons, argon has 18, potassium has 19. Potassium's going to be the smallest because it has the most protons to pull its electrons in. Sulfur, on the other hand, would be the largest. It only has 16 protons to pull in the electrons. So even though they have the exact same electron configuration, they're slightly different in size because of the number of protons. Here are the polyatomic ions. Here are some hints for how to remember them. In class, I'll give you a list of 10 or 15, the most common, the most popular ones that we're going to talk about. It may be beneficial for you to start memorizing some of them, just so that you can do your worksheets and the test more quickly, so you don't have to keep looking at the sheet every single time. But we said before, polyatomic ions are a combination of more than one atom. Some examples here. This is sulfate, and this is sulfite. Sulfate has 4 oxygens. Sulfite only has 3 oxygens. 8 and 8 mean they're oxygens. 8 has more, I think it was hungry, oxygen than 8. They have the exact same charge. The charge is the superscript. That's the upper number right here. Right here, they're both 2 minus. That's the superscript number. And the charge is applied to the whole combination, the sulfur and the oxygen combined, not just the oxygen. But the subscripts, the little numbers on the bottom, only apply to what precedes it. There's 4 oxygens. There's only 1 sulfur because sulfur here does not have a subscript. Here there's no subscript for sulfur. That means that has 1. We assume that this means 1 when there's nothing here. Here this 3 only applies to the oxygen. There's 3 oxygens in sulfate. Common cations. Here's a list. Hydrogen. Hydrogen likes to lose 1 electron. Any of the alkali metals, lithium, sodium, potassium, they like to lose 1 electron. Any of the alkaline earth metals, they like to lose 2 electrons. Aluminum would lose 3 electrons. Here's some examples of your transition metals that have multiple charges. Iron can have a 2+, iron can have a 3+. Copper can have 2 different ones. Silver and gold, usually only +1. Again, they'll be on your list. Common anions. Anions have a negative charge. Cations lost electrons. Anions gain electrons. Things that like to gain electrons found on the right side of the periodic table. Any of your halogens like to gain 1 electron. Sulfur, anybody in the sulfur column likes to gain 2 electrons. Then here's some more polyatomics. Most of our polyatomics are going to have a negative charge. Phosphate, sulfate, sulfite, nitrite, nitrate, carbonate. These are some of those common ones that you might want to memorize. It'll just make your life easier later on down the road.